In this lecture, we shall discuss about the quantum theory of the rigid rotor. Okay, what is a rigid rotor? In classical mechanics and quantum mechanics, a rigid rotor is a three-dimensional rigid body such as a top, a children's toy. To describe the orientation of a three-dimensional object with respect to a three-dimensional coordinate system, two angles and a radial distance are required. If the angles do not vary in time, the rigid body is standing still. When the angles vary in time, the rigid body is rotating and is referred to as a rigid rotor, also known as rigid rotator. A special rigid rotor is the linear rotor, which is a two-dimensional object, a pencil, requiring two angles to describe its orientation. Sometimes one considers rotation of a single particle around an axis fixed in space, and one angle is sufficient to describe the system fully. In molecular physics and chemistry, a molecule can often be regarded as a rigid rotor, which is why the quantum mechanical theory of rigid rotors plays an important role in molecular spectroscopy. An example of a linear rotor is a diatomic molecule. If one neglects its vibration, the diatomic molecule is a rigid linear rotor. More general molecules, too, can often be seen as rigid, that is, often their vibration can be ignored. Rigid rotors can be classified by means of their moments of inertia. For instance, the water molecule H2O is an asymmetric rotor. The ammonia molecule NH3 is a symmetric rotor, and methane CH4 is a spherical rotor. The classical as well as the quantum mechanical linear rigid rotor model consists of 2-point masses located at fixed distances from their center of mass. The fixed distance between the 2-point masses and the values of the masses are the only characteristics of the rigid model. Now, if we draw a rigid rotor, a diatomic molecule will look like this. Say the mass is here M1, and another diatomic molecule, say is this one is another atom, it has mass M2, and if this point is the center of mass and if this rotates about this and with angular speed omega, let us say from the center of mass the distance of M1 is R1 and the distance of M2 from the center of mass is R2. Cm is center of mass. According to this figure, let us consider that the distances of the masses M1 and M2 are R1 and R2 as I have mentioned before from the center of mass, and that the distance between the two rotors is capital R. The distance between the masses M1 and M2 is capital R. Thus, we can write down that M1, okay, let us say M1, the mass, sum of the masses of M1 is capital M, and the sum of the distances of M1 and M2 from the center of mass is R1 plus R2. Let us okay, and this is equal to capital R, because capital R is the distance between the masses M1 and M2. Now for the moment, if we assume that the center of mass is the origin, then we have this one will be M1 plus M2, and this one gives us M1 R1 is equal to M2 R2. So solving this equation and this equation, we get is M1 R1 plus M2 R1 equal to M2 capital R, which is, if we take common R1, then it's M1 plus M2 R1 is equal to M2 capital R. From there we see R1 is M2 divided by M1 plus M2 and capital R. Now if we define the reduced mass, if mu is the reduced mass of the system, of M1 and M2, then we know that the reduced mass actually mu is equal to M1 M2 divided by M1 plus M2. If we substitute this here, then we get R1 equal to mu by M1 and capital R. Similarly, we can show that R2 is mu by M2 and capital R. This is the reduced mass. The moment of inertia of this system is this is M1 R1 square plus M2 R2 square. So if you substitute this R1 and this R2 here, then we get I is equal to M1 and this is mu by m1 capital R square plus m2 mu by m2 capital R square, and this one gives us so mu by m1 plus mu by m2 and here R square. So is this is square, I'm sorry, this is mu square. So we take common 1 by m1 plus 1 by m2, and this is mu square R square. Okay, so then I is m1 m2 m1 plus m2 mu square R square. This one can be written as mu square R square, and here m1 m2 divided by m1 plus m2. So this is mu, and so the mu R square, this is the moment of inertia of the system. Now the kinetic energy of rotation can be written as T equal to half m1, and this is r1 omega square plus half m2 r2 omega whole square. So this one we can write down m1 r1 square plus m2 r2 square, and here omega square. So it's half I omega square, and this is I omega square, but I is mu into r square, so it's half mu over r square omega square, because I is equal to mu into r square. So this is the kinetic energy of rotation of the rotor. Now, but we know that if capital L is the angular momentum of the system, but we know that this is a relation from classical introductory classical physics, that angular momentum is equal to I into omega. This is the angular momentum, and this is angular speed or angular velocity, and I is the moment of inertia. So the kinetic energy then can be written as therefore, so instead of uh, omega, we can write down L by I. So is half mu R square, and this is L by I square. But mu R square is I, and this is L square twice I square. So the kinetic energy is L square by twice I. According to quantum mechanics, the energy levels of a system can be determined by solving the Schrödinger equation. If we solve the Schrödinger equation, then we can find the energy levels. The Schrödinger equation is Hamiltonian of the system wave function, and this is energy eigenvalue, and then psi. This is the Schrödinger equation. And if there is no potential energy, then H can be written as T only, right? So it's zero potential energy, and T can be written as L square by twice I. We have found out T equal to L square by twice I from this. Also, we know that also the Hamiltonian operator is actually minus square square by twice mu, where mu is the reduced mass del square, and potential energy is 0, so we do not need that term. In spherical polar coordinate system, because we need to express this del square operator or even L square operator in terms of theta phi. In spherical coordinates, it can be shown that this operator is this. Okay, and we consider the rigid rotor problem to a rotation in 3D corresponding to motion on the surface of a sphere of radius capital R. For constant radius, small r, let small r equal to capital R, then there is no variation with respect to small r, because this r is constant. Small r, and we have then the del square operator is 1 by r square, and sin theta del by del theta, sin theta del by del theta, 1 by r square sin square theta, del square by del phi square. Thus, the Hamiltonian operator H can be written as and here this is a function of only theta and phi now, which is minus h square by nu del square. So is minus h square by, I'm sorry, this is twice mu and twice I, and can be written as minus a square by twice I, and then 1 by sine theta d by del theta sine theta del by del theta, and 1 by sine square theta del square by del phi square. But which can be written in terms of capital L square as we know that the square of the angular momentum, we know that angular momentum square is minus h square, and this is 1 by sine theta del by del theta sine theta del by del theta plus 1 by sine square theta del square by del phi square. So if we use this here, then we get, therefore h can be written as L square by twice I, which actually we have found out before. Since the Hamiltonian does not depend on the radial distance for a constant capital R, the wave function will depend only on the angular variables theta and phi. So the wave function is is a function of theta and phi only. And the Schrödinger equation then can be written as minus a square by twice I and 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square, and here psi is equal to E psi. The solution the above equation is nothing but the spherical spherical harmonics. The solution of the above equation are the spherical standard spherical harmonics. Y, L, M, theta, phi. The solutions they satisfy the eigenvalue equation. So it's 1 by twice I, and that one was capital L square. So it's Y, L, M, theta, phi is square here L into L plus 1 and Y, L, M, theta, phi. We note that the energy does not depend on the magnetic quantum number small m. L is the orbital angular momentum quantum number. And m is known as the magnetic quantum number. The energy eigenvalues are EL is square by twice I, here L into L plus 1. The quantum numbers take values where L is 0, 1, 2, like this. We'll continue. And M is 0, plus minus 1, plus minus 2, and up to plus minus L. The spherical harmonics Y, L, M are related to atomic orbitals in the hydrogen atom. Notice that the phi term in the wave function is the same as the 1D rigid rotor wave function. This implies that the spherical harmonics are eigenfunctions of the Lz and L square. This Y, L, M of theta phi are eigenfunctions of simultaneous eigenfunctions of L square and also Lz, z component of the angular momentum, such that L square Y Lm, and this is L into L plus 1 square Y Lm, and Lz Y Lm, and this is M squared Y Lm. We can list few spherical harmonics here. Few Y00, which is, these are listed, these are actually standard. You can find all these in different books. Y10 is square root of 3 by 4 pi, and this is cos theta. Y1 plus minus 1 equal to square root of 3 by 8 pi, and sine theta e to the power plus minus I phi. Y20 square root of pi by 10 by 16 pi, and then 3 cos squared theta minus 1. Y2 plus minus 1 I square root of 15 by 8 pi, and then cos theta sine theta e to the power plus minus I phi. And the last one we list here, but you can continue. These are listed, standard spherical harmonics. This is 2 plus minus 2 is equal to square root of 15 by 32 pi, and this is sine squared theta, and e to the power plus minus twice I phi. We can plot the polar plots of the spherical harmonics, give the angular distribution of the particle. We note that for capital I, equal to 0, the only possibility is m equal to 0. The corresponding spherical harmonic function y00 is independent of theta and phi. It is just a constant. This one. Independent of theta and phi and is spherically symmetric. For L equal to 1, m has 3 values. M equal to 0, m equal to plus minus 1. For L equal to 1 and m equal to 0, the function is proportional to cos theta. And this implies that the function is maximum along theta equal to 0 or the z-axis. For L equal to 1 and m equal to plus minus 1, the functions have maxima in the xy plane. And so on. Okay, we would like to stop here. This is for today. In the next lecture, we shall discuss the quantum theory of hydrogen-like atom.